Okay, lecture 24. In this lecture, so what is pre-recorded, I would like to discuss about the future of DTCO, Design Technology Co-Optimization. So, lecture material has been covered more or less completely. So now we have to talk about future in this lecture, and the last one, lecture 25, will be devoted to the presence of the DTCO activities. It means that I will review IDM papers related to the DTCO activities. Okay, so let's go. Okay, so please have a look at this workflow of a DTCO, especially the one focused on TCAD related jobs. So as I told you repeatedly, when we say DTCO, there are many different flavors. So for example, if you are working with layout engineers, then maybe they will say that they are doing DTCO. And also, if we are working with the device engineer actually fabricating something, then they also would say DTCO. Mine shown here is more related to the TCAD centric one, and also maybe suitable for so-called pathfinding DTCO. So when we don't have any kind of silicon data, then we can do in early stage engagement for technology development, and that is, in that case, TCAD plays really a critical role. So we have covered this processor emulation and device simulation. Due to time limitation, we were not able to consider this compound model and extraction and even circuit simulation, so sorry about that, but we have covered the core part of this TCAD engagement. My question is then, this is more or less well-established workflow. Then what is the next one as a future of a TCAD? So I would like to say two different directions. One is how can we accelerate this existing DTCO workflow? So as you know, this one takes really long time, because processor emulation takes time and device simulation takes time, also extraction that takes time, and also every step takes its own time. But in many cases, most time consuming ones are regarded as these, so we have to accelerate their numerical efficiency. It means that if this procedure, DTCO workflow, is greatly accelerated, then its applicability can be also expanded quite significantly. So then, this is not just a reduction of time, but it can make another stage of its application. So in this sense, I guess that the role of a GPU is quite impressive. So please have a look at the conference presentation material press released by Synopsys, the leading company in this TCAD and EDA scene, and it released the press release on March 18th, 2025, just about 9 months ago. So the venue was actually, I guess, that NVIDIA AI conference, and it says that early result applying GPU-enabled capabilities and NVIDIA CUDA-X libraries to the Synopsys Central TCAD process and device simulation solution is projected to accelerate the time to result up to 10 times. So 10 times means that if it took, for example, 24 hours, so just one day, then it becomes 2.4 hours, so which it can be really accessible to everyday engineers. So the difference, 10 times difference is really a big deal, and by using GPU enabled capabilities, yes, they can accelerate quite a lot. Of course, this slide itself is not for TCAD programs. It is for other EDA program. I have no idea what it is exactly. However, it says that by applying this GPU, so in previous versions of GPUs, so there was 5 times, 10 times, 15 times acceleration, and with their latest, NVIDIA's latest hardware, Blackwell, they were able to obtain 30 times increase in numerical efficiency. That's great. And I guess that anyhow we have to concentrate, or we have to pay attention to the acceleration of this simulation, because we have to do this job again and again repeatedly till the end of this optimization job. Okay, this is related with the Synopsys, the leading company in this TCAD scene. And also, we can have another activities from TSMC, the leading company in foundry service. TSMC presented also a similar presentation in NVIDIA DTC, that is AI conference. And in this case, they have shown many slides, but I just took 2 of them. One is GPU accelerated multi-grid solvers. I guess that this and that are quite much closely related. In the core of every numerical simulation, as much as TCAD is involved, so although underlying physics can be different, but after discretization and some treatment, eventually we arrive at the matrix solver. So solving a set of linear equations. That is the central job of TCAD programs. In that case, NVIDIA acceleration, GPU acceleration scheme can provide us significantly faster matrix solver. So that's the problem. If that most time-consuming part, the matrix solve part, can be accelerated, then without paying much effort on modifying the code, just matrix solver library can accelerate the entire TCAD simulation quite aggressively. I guess that this is related with that one. Also, that is related with this Synopsys announcement. And another one related with our course more closely is this one. So topology simulation. So topology simulation is a different name to say process emulation. And if you have a look at this part, then now we wanted to talk about, for example, etch of a certain thing or deposition of a certain thing. So in that case, actually we have not considered gas phases, just to consider the surface evolution in our lecture material. However, in reality, to be more rigorous in describing the procedure, then we have to consider the gas phase. So also we have to consider the reaction between gas phase molecules and surface atoms. So in that case, we have to consider the particle movement of a particle and existing structure and their particle movement and reactions. All kinds of these things should be considered for more advanced simulation. I guess that this is related with the etching. So here you can see that is these are obtained from this double patterning or quadruple patterning, and we are now sending certain etchant, and it just to make this fin. Yes, that is a typical one we have to do for process emulation. But when you have a look at this upper law, then you can find that this is very much related with or quite similar to the computer graphics. So computer graphics, we have a certain three-dimensional shape, and we wanted to project it to just two-dimensional, to just visualize in the monitor or any kind of visualizing instrument. So in this case, we have to consider the ray generation. For example, let's say that there are a certain light sources all around this scene, for example, sunlight or different lighting instrument. In that case, in order to generate more realistic computer graphics result, we have to trace the ray. And the ray is, it is reflected by the existing surface, and it eventually blurred and change the shape or brightness of that position. So this kind of a thing, although the physical entity is not the electromagnetic photon, but this particle, but since both of them have a straight trajectory, so it is they are quite similar in that sense. So they are trying to adopt this already existing computer graphics algorithms to enhance their topological simulation. I guess that this is also quite important to enhance numerical efficiency of our process emulation. So simply speaking, if we consider future of DTCO, then in my opinion, the critical point is its slow speed. So we have to accelerate this entire DTCO. Since the speed is bottleneck of application of DTCO framework, so if that can be accelerated, then I hope that more and more engagement can be found in real industry. That was one direction. So make it faster than ever. Another one is variability and manufacturing. So in many cases, and also in this semester, we consider the nominal device, the very typical one, the target device we wanted to fabricate eventually. However, in real manufacturing, we cannot perfectly control the variability. For example, please have a look at this SEM image taken from one research article, and in that case, they tried to draw 20 nanometer pitch silicon fins, and these 5 pictures or SEM images are taken from 5 different positions in a sample. In the same sample, we have this kind of images. So the one you can immediately understand is, although we want to draw these straight lines, but they are not straight at all. And also the pattern shown here and pattern shown here, here and there, they are not identical. They show their own shapes. So if we consider the most ideal structure, straight line displaced by 20 nanometer pitch, then all of them just show some deficiencies. However, that is the real one. Of course, I'm not that sure the real pattern is so much shaken, but anyway, it is true that our capability to control the process is not perfect, so we have to consider variability. So even though we try make a certain one, but the real result can be slightly different from the ideal target. There can be many different variability sources, and the relative importance of each variability source may differ. So I remember that when I was a graduate student, so at that time, random Doppler fluctuate. Sorry about that. This is typo. Fluctuation was one of the most important variability source, because at that time the device was planar, and also we had no other way to control work function. So the only way was introducing more and more impurities in it. Also, therefore, at that time, dopant fluctuation, random dopant fluctuation, was regarded as most significant variability source. But in these days, we wanted to reduce random dopant fluctuation as small as possible. So for that purpose, we just introduce only small amount of dopants into the substrate. And line edge roughness, so this is quite shown here. So although we wanted to draw a straight line, the actual line sometimes shows differences, deviation from straight line. That is still important in these days. And work function variation. So work function variation means that since we now have quite a small structure, so work function metal has inside it, it may have different grains, and different grains can contribute to different work function values. So this grain gradient work function grain contribute to the variation of work function. So that really makes a big problem in our advanced node. So this is quite important one. And also I have told you that inner spacer, importance of inner spacer in nanosheet era, and also inner spacer is just its thickness is controlled by sophisticated etching process, not patterned. So if we have different so if we have a variation in the inner spaces thickness, also that will introduce much different behavior in our device. So manufacturability is directly related with variability. We wanted to make identical devices, several billion copies. However, if that is not possible, then we have to minimize the variation, or at least our design should be aware of that variability and made within that range. So in that case, I guess that nowadays people are much interested in the concept of a digital twin. Actually, the concept of a digital twin was coined about 20 years ago, and I have heard about this word again and again. But at the initial time when I heard about it, then I was not able to understand the difference between TCAD model and digital twin, or TCAD model accelerated with AI technique and digital twin. But let me just summarize my understanding on their differences. So we have we have covered the TCAD models in this semester. So it tried to generate high fidelity physical simulation. Of course, you may say that process emulation is not simulation, so we do not care about the detailed physics inside it. Yes, you are right, but anyhow, compared with the digital twin, so still process emulation try to mimic the progress of a surface shape. So therefore, it can be regarded as a high fidelity physical simulation. And when we do the TCAD simulation, we expect that it may take several hours or even days. So it is not actually related or directly connected to the fab. So fab are running, but in the R&D process, we are sitting in our office room and just to talk about how can we improve the performance of our device by using the TCAD model. So it is not entirely connected to the fab, and whenever you do that there is no real corresponding one. So in this sense, data flow, no real-time data, and updates means that let's say that we have some silicon data. The device performance is measured. However, in order to implement that data into our TCAD model, then what we have to do is just change the internal material parameters. Okay, so in this time, maybe scattering is enhanced due to certain reasons, so we have to increase certain scattering parameter. That is way we change the TCAD model. Then change in these parameters will result in difference in our simulated data, but this is not immediate one, so we need learn the simulation and again, and also calibration is required. So up to now, I have thought about seemingly disadvantage of a TCAD model. So the TCAD model is not for real-time use. It is used especially in the R&D phase. So how can we generate the next generation device technology? In that case, so this TCAD model provide us really valuable information about what should we do to design a new technology. However, when we talk about digital twin, this is a different. This is a real-time virtual replica of something physical reality. So in many cases, if we look at papers, then what is the physical reality? Many cases from the viewpoint of semiconductor manufacturing, the physical reality can be an equipment. So, for example, etching machine or deposition machine, other kind of ion implantation machine. A different semiconductor fabrication equipment can be regarded as the physical reality of this digital twin. Then we typically wanted to make its virtual replica, and from that machine we sense its operational data, and that data is measured in real time and sent to its digital twin. So it is always try to align with its physical reality, and always to represent the physical reality's current status. So therefore, data-driven automated update data is happening every time. So where can we use it, or where can we use this digital twin? So use case is manufacturing control. So equipment can show some variation time to time, and if we have a digital twin to a certain equipment, then we can monitor its difference and say that, since the equipment shows a little bit different behavior, then we have to control the operational conditions to still have acceptable result. So this kind of manufacturing control or predictive maintenance. Predictive maintenance means that this equipment shows some continuous reduction of certain productivity. So maybe within several months there will be certain problems in this equipment that can be detected. And also this is quite efficient in its numerical calculation, so we can use it for system optimization. Okay, instead of the current configuration, why don't you just swap the position or placement of these equipments? So as I explained up to now, in many cases digital twin is related to fab when we apply it to the semiconductor manufacturing and equipment. However, in my opinion, so the target system is, in the case of TCAD, we are more or less interested with the device itself, the shape, the chip we will use. And in this case, digital twin case, we are interested the equipment to fabricate the chip. However, I think that we don't have to limit ourselves or restrict ourselves only to the equipment maintenance or control. Also, if that is related with a certain model for our feature size or device, then they can be combined. And eventually the reason why we wanted to develop this digital twin is eventually generate the working chip with a higher yield. So they are not isolated, but we have to combine them. Then for that purpose, this model, TCAD model, should be more effective. I mean that not only just numerical or physics-based description of the feature size difference, we have to also consider more efficient, simply speaking, AI-related way to describe that one. When we have TCAD and or equivalent AI powered model, then this one can be more well collaborated with digital twin. Then if we have this kind of use of models or twins, digital twins, then I hope that eventually that can greatly contribute to the increase of eventual yield or effectiveness of our semiconductor manufacturing. So in my opinion, that is another future of DTCO, not just confined on this DTCO framework, but that should be aligned with the actual manufacturing, and we can get even bigger advantages out of it. So that is one way. Okay, so that's all for my short lecture on my expected future of DTCO activities. And as I told you at the beginning of this lecture, the last one, lecture 25, will be devoted to the review of presence of DTCO. What we are doing related with DTCO in IDM 2025. Okay, then see you later. Thank you. Bye.